welcome everyone in person and whoever is online joining us today for another one of our ACOM seminar series. Today we've got Yunqian Zhu, who's coming and visiting us from just down the road at LASP and CIRES. Before I get into a little introduction, I'll just say, because we're doing a hybrid seminar today, for the folks in person, we'll hand the microphone around at the end for questions, but folks online can do Slido like they normally do. And I think that's probably the only formality we need to cover for hybrid today. So just a little background on Yunqian. She did her PhD at CU in both ATOC and LASP with Brian Toon, looking at polar stratospheric clouds and WACM using the KARMA model, and also looking at observations. I think some important findings that have motivated some model development in the last few years. She was here in ACOM for a few years during the pandemic and is now back at LASP and now at CIRES as a research scientist. And one of the reasons I asked her to give this talk today was about the Hunga Tonga eruption, which was a very unique, I'm sure you're going to hear about, volcanic eruption that's had a lot of important impacts globally. But I'm excited that she's more generally also going to talk about the general impact of volcanic eruptions on stratospheric chemistry and aerosols. So thanks for coming, and hand it over to you.
Hello, everyone. My name is Yunqian. I'm from LASP and CIRES and NOAA. Today, I'm going to talk about the impact of volcanic eruptions on stratospheric chemistry and aerosols. I will start with a background introduction of the stratospheric aerosol layer. It's a layer around 20 to 25 kilometers above the tropopause. So how does this form there? One of the sources is the injection of the volcanic eruptions that directly inject the SO2 into the stratosphere. There are also tropospheric sources like OCS, SO2, and DMS from the biomass burning ocean and anthropogenic emissions. Those OCS and SO2 get transported into the upper troposphere or directly into the stratosphere through the tropical convections, as well as some other convection, such as the monsoon convection. So in the upper troposphere and the stratosphere, those precursors can convert into the gas phase H2SO4. And then, because of the cold temperature up there, it nucleates into the sulfate aerosol. Then the newly nucleated aerosols can coagulate and grow into a bigger sulfate aerosols. Those stratospheric sulfate aerosols transport to the polar region, and during the polar winter time, it grow and nucleate and form the polar stratospheric clouds, known as PSCs. There are other sources for the stratospheric aerosols, such as meteoric dust that's coming from the space. So those meteoric dust can act as a nuclei for the sulfate and the PSC's formation. There are other tropospheric aerosols that get transported into the upper troposphere and also the lower stratosphere, such as black carbon and organic carbon. So the recent ECLIP campaign that led by NCAR, Laura Penn, and that's one of the goals is investigating those aerosols that get transported up there. So my research also involves in this volcanic ash that's injected by the volcanic eruptions into the stratosphere. So before I talk about the Tonga, I will talk about the other research I did 2 years ago on the 2014 mountain Kelud eruption. This eruption is special because it injects a lot of volcanic ash into the stratosphere. So volcanic ash is currently usually neglected in the climate model simulation because the ash particles are usually considered to be large, high density, and short-lived in the atmosphere. However, many observations show that it is not always the case. 8 months after the 1991 Pinatubo eruptions, near about 11 kilometer altitude, you can see they observe those sulfate-coated ash with odd shape. Another eruption, 1 year after the 1963 Mount Argon eruption, volcanic ash can still be observed around 20 kilometers. 1 year after the 1982 El Chichang eruption, inside the Arctic stratosphere, the aircraft captured those odd-shaped, large volcanic ash particles. So this motivates us to look into the volcanic ash and their potential impact to the stratosphere aerosol layer. Back to the 2014 Mount Kelut eruption. We look into this eruption because the modern observations have lots of new and exciting observations available. In 2016, Jean-Paul Vernier reported that this eruption have the volcanic aerosol layer lasting more than a month. It is not surprising we observe volcanic aerosol layer for so long, but it is exciting to see that this layer is not just a sulfate layer. So from the depolarization channel showing on the bottom, you can, if it's sulfate layer, it will be all like a blue color, but you can see it has some green and yellowish color there. This means those particles are not round, but with odd shape, like volcanic ash. So we are using the vacuum karma model to simulate this persistent volcanic aerosol layer after this eruption. This panel shows the backscatter coefficient as a function of time during the first 20 days. We are trying to reproduce the evolution of this eruption. And our model simulation is in blue, and the observation, Calypso observation, is in black. And for a reference, the red dot line is a background, Rayleigh plus the sulfate. So after 20 days, I did a zonal average for the model and the Calypso. So the take-home message is that after 60 days, we still see the backscatter above the background layer for both model and observation. So with the model, I look at the composition of what we simulated. This figure shows a backscatter coefficient contribution from the pure sulfate in blue and from the mixed particle mainly containing ash in red. You can see that the mixed particle containing ash dominate the simulated aerosol optics for the first 2 months. So the question is that how could ash persist so long? Is it because they are very small, like micron-sized sulfate particles? The HRAX observation is another valuable source we investigate the particle size distribution. This figure shows the particle size distribution. The black line is the A-track aircraft observation that made 1 month after the eruption in a nearby island, Guam. You can see the A-track sees all those particles that's above 1 micron size. With the model, I initially did this test with only the pure sulfate injected. And you can see we cannot reproduce any of the micron-sized particles here. Then I'm adding the volcanic ash that's assumed to be volcanic glass. That's about 2.3 grams per cubic centimeter for the density. And we start to reproduce a little bit of the super micron-sized particles. However, we are still missing all the particles that's above 5 microns. Then I assume a lighter ash density of 0.5 gram per cubic centimeter. And you can see that our model simulation matches the observation really well. So those ash particles are the pumice, who is more porous structures, has a much lighter density than the volcanic ash, volcanic glass. So another interesting thing we investigate for this eruption is the SO2 lifetime. This figure in Karn et al. 2016 shows a correlation between the altitude and the mass of the injections and the lifetime of SO2. You can see those triangles represent the size and the eruption size. The bigger the eruption is, the longer the lifetime is. Also, if the altitude goes higher, the lifetime goes higher. So this is an observational fact. However, in the climate model simulation community, we often think the SO2 lifetime is about a month. So that's why we look into this Kelud eruption. And we did a vacuum simulation with default setting. And it is produced a SO2 lifetime of 26 days. However, the observation shows the SO2 lifetime for this eruption is only a week. So the main mechanism for the SO2 depletion and SO2 lifetime is controlled by the OH. Inside the volcanic plume, the OH can be quickly depleted, and it takes time for the OH to be reproduced. So the lifetime is quite long. So one of the reasons for the short lifetime in the observation is because the observation cannot detect all the SO2. Once the SO2 plume is more scattered, it merges to the background and below the detection limit, so the observation cannot see it. So firstly, we subtract the SO2 below the OMI detection limit. From the model, we are getting a SO2 lifetime of 13 days. You can see we are getting closer to the observation, but especially the first 10 days, we still have very large discrepancy. We actually tried many methods, like injecting to different altitude or injecting to different area, size of the injection area. But none of those can successfully to reduce the SO2 lifetime. So eventually, we consider a heterogeneous reaction of SO2 on ash particles That is, as has been reported by many lab experiments for a long time, but hasn't considered in a climate model before. So we successfully to reduce the SO2 lifetime to 7 days as observed. So a little bit detail about what this reaction is. So SO2 reacting on ash particle is a chemical process rather than a physical process. So here's a schematic graph that we have the mineral ash and the SO2 particles through a process called adsorption, and the SO2 can directly stick on the mineral ash on those available sites. And this process is very rapid with no barrier, unlike the nucleation process that take time and we have to go over some barrier to have that reaction happening. And then SO2 oxidized to become the SO4, which is a sulfate that stick on the ash particle. Another thing is that once all the available sites on the mineral ash are taken, this reaction stops. So unlike the growth process that can continuously take more and more SO2 as long as the vapor pressure is saturated. So back to the SO2 lifetime plots, the conclusion is that both the actual SO2 lifetime is between the original simulation and the observation. So it's about 17 days in the model simulation. So the last part we investigate is whether if the ash can impact the stratospheric sulfur burden after the eruption. The blue line is a test with no ash injected, and the black line shows we have the ash injection, and we allow the microphysical interaction between the sulfate and ash. You can see that these two simulations have not much difference, which means that before all the after all the ash falls, it hasn't taken much sulfate with it. So once we add the SO2 heterogeneous reaction on ash, we find it increased the removal by 50% within 60 days. So in conclusion for this part, we have to modify the diagram of physical and chemical processes in volcanic clouds. So during the volcanic eruption, we have ash and gas SO2 injected. We all know that ash can sediment very quickly. At the same time, the SO2 react to form the sulfuric acid and form the sulfate aerosol. So this research suggests we should add the SO2 reacting with ash particle to form the mixed sulfate ash aerosol. And those aerosols can also interact with the pure sulfate. And then large ash particles sediment with sulfur to reduce the stratospheric sulfur burden. And the micron-sized ash particle will persist with sulfate to last longer in the stratosphere and impact the climate in a longer term. The second part of this talk, I will talk about the 2022 Hunga Tonga eruption. And we are currently have a paper under the final review at the Communications, Earth and Environment. This eruption is very special because it is a submarine volcanic eruption that bring a lot of seawater and inject it into the stratosphere with the SO2. I will start with a storyline of the water and the aerosol evolution from our CSM model simulation. So in the model, we inject the SO2 and the water into the stratosphere. Because of the large amount of the water, and some of the water stay in the water vapor phase, and some of them form the ice cloud in the stratosphere. Because of the abundant water vapor, it provides a lot of OH that can react with SO2 to form the sulfuric acid. The sulfuric acid then nucleate and coagulate to form the sulfate aerosol. Also, because of the water vapor, there's a hypothesis that the swelling of the aerosol can make the aerosol become getting bigger. So in our project, we try to answer the following scientific questions. First, how much water was injected and ice formed during the initial phase? What does the water vapor mean for the SO2 lifetime? What's the process that controls the sulfate particle size, the coagulation or swelling? And with only 0.4 teragram of SO2 injected, which is a relatively small eruption for the stratosphere, how long will this eruption affect the climate system? We start the simulation by looking into the MLS observation of the water vapor. Louis Millen et al., 2022, shows about 150 teragram of water was injected during the eruption, which increased the stratospheric water by about 10%. So first, our model simulation, we try to match the MLS observation for the first 3 months. And you can see we did quite a great job matching the anomaly. So then we find out we have to inject about 150 teragram of water. And then during the first 2 days, there are about 20 teragram of ice formed, and about 10 teragram of ice fall out of the stratosphere. And eventually, we have 140 teragram of water vapor persists. And this 140 teragram of water still persisting now in the stratosphere. So one of the interesting discussion when we just see this eruption is that the satellite observation from Calypso sees abundant sulfate aerosol right after the eruption. So this abundant, it shows a very high backscatter with very low depolarization, which means those are the sulfate particles. It is surprising because SO2 usually take more time to be oxidized to form the sulfate aerosol, not within 2 days. So we try to find out what's happening to create that this eruption creates such a large backscatter during the first 2 days. So still, we look back into the SO2 lifetime here. So this shows the SO2 burden as a function of time after the eruption, and the symbols are the observations. And we have one case that we only inject the SO2 in the stratosphere, showing that we are the model creating a lifetime about 28 days, which again near a month. And then we inject the water along with the SO2, which significantly reduced the SO2 lifetime to about 12 days. That match the observation really well. This is because the OH reaction with SO2. So the left figure shows the SO2 only case that the OH get depleted very rapidly in the plume. And on the right side, because of the water, the OH is not depleted inside the plume. So it can continuously react with the SO2 to shortening the SO2 lifetime. So in conclusion here is that the water injection significantly shortens the SO2 lifetime by providing abundant OH. So back to the Calypso observation. We did 3 model runs on the left side to compare with the Calypso backscatter. The first panel shows the model case with both SO2 and water injection. And we can see that this case can reproduce the observed high backscatter 2 days after the eruption. And if we only injected the SO2 without the water, it produced very little backscatter, as we expected. We also did another sensitivity test that we double the SO2 injection. In this case, it's still not able to produce any backscatter that close to the observation. So we are pretty confident that because of the water vapor, we are getting a lot more backscatter from the aerosol. So this, besides the Calypso, we also compared with the ARMS observation, which measures the extinction of the aerosol plume. The first panel shows the ARMS observation from the first 1.5 months. And then we have the SO2 only case in the middle, and then the SO2 plus water case on the bottom. You can see that with the SO2 and the water injection, we are able to produce the extinction that almost double the extinction of the SO2 only case. And we also investigate here that whether this increasing of the optical property is because of the swelling of water or because of the coagulation. On the right panel, it shows the effective radius of the SO2 plus water case, and you can see this case is producing the particle about 0.3 micron. Without the water injection, it only produced the particle size about 1.5 micron. And then if we look at the weight percent inside the particle, with the water injection, the particle mass only increased by about 15% because of the swelling of water. This amount of swelling of water cannot explain the large increase of the effective radius. So we think that because of the short SO2 lifetime, coagulation creates larger sulfate particles that double the stratospheric aerosol optical depth. And the swelling of water contribute a little bit, but not a major contribution. So then we did a seasonal forecast for this eruption, and we predict we run the model until October 2022. to show the evolution of the water plume and the sulfate. You can see as the time goes, the plume is the measure of the plume for both water and the sulfate are transporting towards the Antarctic and hanging outside the polar vortex. And by December, we can see a lot of sulfate is getting into the polar vortex and like double the background sulfate. So here is the zonal average plot. Sorry. So the first figure shows the water increasing in late September. And you can see we still have 2 to 3 ppm V of increasing of water compared to a background water about 6 ppm. And then we have the surface area density increase, mostly outside the polar vortex, but still have some transport inside the polar vortex, about 2 to 4 micron square per cubic centimeter, compared to the polar stratospheric clouds. We generally have the surface area density of 10, and background sulfate about 1. And here's another mechanism we think that water vapor may be due to this, for this eruption to the ozone depletion. So this figure shows the chlorine activation reaction between the ClO2 and HCl. You can see if we increase the water vapor from 4 ppm V to 7 ppm V, the reaction probability for this reaction increased by 1 order of magnitude. So the enhanced aerosol surface area density and the water vapor may have an impact on the ozone chemistry this year. So for conclusion, that the water vapor injection and a small amount of evaporating ice deposits a substantial water vapor in the stratosphere after the Hunga Tonga eruption. And the large water vapor abundance result in the formation of OH, which acts to speed up the conversion of SO2 to sulfate. Because of the fast formation and coagulation of sulfate, particles form with larger sizes and a larger extinction than the one without water injection. We predict the water vapor and aerosol that get transported towards the South Pole will linger near the polar vortex until at least right now. Thank you. Oh, perfect.
All right. I'll go Bill first.
Really nice talk. And good,
Thank you.
Great explanation of everything. Something I don't understand. You come up with a time scale of like 12 days for the SO2 lifetime, but then you're showing those Calypso profiles on January 17th, which is like day 2, and you've already got a lot of sulfate. So
Yes.
So how do you get sulfate in 2 days if the lifetime is 12 days? Am I missing something?
Let me think how to. So like it constantly converting the SO2 to sulfate. And so from this figure, you can see that at the beginning, it's like flat here, the first 2 days, I guess.
So there wouldn't be much sulfate. It would take
Yeah. So like with this much dip, it can create that amount of sulfate. Like
it'll just make a little bit, but that's enough
Right.
to match the Calypso observations?
yes.
Okay.
Yeah. Yeah, it's a log scale. Yes, that's right.
Ah, log scale. Okay, thank you.
All right.
Well, my first question is also on this plot. What is that dashed line? You didn't talk about that.
Oh, okay. So the dashed line is to match the observation by subtracting the modeled SO2 with a detection limit. So I subtract all the SO2 below the detection limit to get this dashed line, which also shows that this eruption, the first 20 days, the plume probably very compact, that the lifetime doesn't, the SO2 is not below the detection limit that much, because the dashed line and the solid line are very close.
Oh, thank you. I had another question about the Kelut eruption. It seemed like you have to know, in order to match the observations, you have to have an idea of both the mass of ash and sort of the structure of the pumice to know like how much surface area is available for SO2. And I'm just wondering, are those things you feel you know well, or were they like free parameters you used to get to the right answer?
So first, to answer that surface of the pumice, so in the laboratory experiment, the chemical surface area is about 100 times more than the physical surface area, for assuming it's round. So they did many collection of the samples, and the estimate it's about 10 to 100. So I use that range for estimating how much surface area I'm getting for one particle. Because in the model, I know the surface area of a round ash particle. That's what I assume. And for the ash, it is very difficult to reproduce what the original ash injection is. And so that's like I did like 100 simulation, and I tried to, so this is a, whoops, where is it? Oh, okay, wait a second. So this is a line, and this left one is, I'm injecting different amount of ash and with different size distribution and a different density, and did like 51, and then try to find the best estimation of the ash injection. So the cool thing is that like no matter how I inject, what's the size distribution initially, I assume after like 2 weeks or so, the size distribution start to form depend on the density. Like it form a certain size distribution of the ash particle based on what density I assume. So initially, like the lower one will quickly coagulate towards the medium size, and the large one is falling, so it's only half that size distribution is left in there.
Thank you.
Thanks.
Anyone else have any more questions? Oh.
I have a question about the amount of water vapor that you assume in your initial cloud. What's the mixing ratios you're putting in your model in those layers where the chemistry happens?
Sorry, I deleted that slide. Maybe I can find that. Is that okay? I find another slides. Well, I'm trying to find that slides. Maybe this one. Okay. Okay. Okay, so this is an injecting profile. And so the black line is the saturated H2 mixing ratio. Like you can see at 20 hectopascal, it can hold about 2,000 ppm of water without ice formation. And at 30 HPA, can only hold 500 ppm of water. And the injection mixing ratio is in the blue line. So I like kind of try to match that MLS in a month, and then this is the initial injection I come up with. And you can see below the 15 millibar, and there's a lot of getting saturated. And because of the expanding of the plume, a lot of them evaporated right away in the stratosphere without falling, but some of them also falls. So if that's answer your questions, no or
Yes,
no.
that does answer my question. And
Okay.
we do just have some observations to help you with exactly that assumption.
Oh, okay,
So yeah,
cool,
I'll talk to you soon.
yeah.
Yep.
Did you look much at the halogen chemistry in the volcanic plumes?
The initial halogen chemistry, when we start this project, we looked into it, but we did not see the ozone depletion that's caused by the halogen chemistry. That we put a little bit of HCl in the plume, but it doesn't create much ozone depletion. But the ozone depletion is observed by the satellite. So I think that's one thing that still people are investigating. If you want to know about the ozone chemistry in October, and our CIRES is working on that. Yeah.
Sure.
So you talked about the Kelut eruption and the lifetime of SO2 decrease from maybe a month in the model to a few days, 7 days. How about just background ash in the atmosphere? Do you have any idea just by having that in the model chemistry how much that reduces the SO2 compared to this gas phase loss?
Background ash.
Yeah, there's going to be ash, floating around in the lower stratosphere all the time, right? Small amounts, or is it just always just it's only there, after eruption, and then gets washed out?
Oh, you mean if the volcanic ash can persist on the background, or?
I'm
I don't
just
know.
asking basically, how much ash is, in the lower stratosphere, all the time. Relative to, after a volcanic eruption where you have a lot and it, decays away. Is that amount of ash important for any of the SO2 oxidation chemistry, or is it just too small relative to the gas phase?
I don't know about how much actually ash on the background, but like for the observation point, like, it's not this one. Oh, it's a different slide, okay. Like the Calypso, right? Yeah, for Calypso, it's seeing this depolarization that's from this volcanic plume. But like at least Calypso cannot see. Calypso is not very sensitive, but it cannot see the background or ash persisting there. So I have no knowledge about background ashes.
Okay.
There
Well,
in
I
the
mean, the model
stratosphere.
could probably, you could look in the model and see what you have, and you could see what impact that has, but it must be small. is what you're saying.
If you talk about the tropospheric aerosol that's getting into the stratosphere, the dust is usually not getting into the stratosphere because they are the primary aerosol. It gets washed away very quickly in the lower level, and it has very small amount transported up there. And sulfate, on the other hand, it goes up because it's like a secondary aerosols.
Okay.
Yeah, if that's
Thanks.
kind of, yeah.
There'd be meteoric dust and some smoke from wildfires, but those are both chemically different from pumice, I think, that you're studying. So I don't know.
Yeah, like the fire, it has to have fire happening, and meteor dust, I think it's usually already coated with sulfate once, because it transports down, and like Mike has some simulations of that.
Hi. In the introduction, you mentioned the OCS is also produced in the plumes. I wonder if in the model is already the oxidation of OCS into SO2 is in the model, and is it very different for every volcano, or how do you do that?
So you mean the OCS become the sulfate? How
Or
the OCS?
for SO2,
SO2.
OCS to SO2, is that
I
is
think
that one
so,
product?
right? Mike? So my knowledge is that OCS is pretty stable in the troposphere, and then it gets transported to the stratosphere, and then because of the photochemistry, and it becomes the SO2. But Mike has more knowledge about it.
Three reactions. OCS breaks down by photolysis, reaction with OH, and reaction with atomic oxygen. And all of those form SO2, I believe.
For every volcano, you have different amount of OCS.
What's that?
For every volcano eruption, you have different.
Volcanoes don't really put out OCS. It's
Right.
produced at the surface from different processes. Some of them are bacterial and no. Yeah.
Right.
Any other questions? I have one. Can you go back to that OMPS sort of data comparison where you showed the evolution in like latitude, time? Yeah, so should I interpret from this that does CSM have too little horizontal transport mixing? Like, I'm guessing what's happening
Yes.
maybe in the models, it's going too vertical and not enough horizontal, or is there maybe a chemical process?
Yes, we are always discussing this with every volcanic eruptions, that the horizontal transport, especially transport crossing the tropics, is difficult in the climate model simulation, such as CSM. And I also see other models have the same problem. In the stratosphere, once it passes the 30 or 40 degree, and the horizontal, it's a meridional wind, is much stronger, and it can actually transport closer to reality. But in the tropics, the meridional wind is very small. And like either the model is missing some turbulence or like some vertical wind shear that happening in the bring by the volcanic eruption itself, or like in the background that like in the tropical area that the climate model cannot resolve. That's what we think that makes the climate model have harder time to transport the plume.
And what level is this at, or is this like a?
So this one is about 30 millibar.
Okay.
Yeah, but other volcanic lower also the same. Like with the Kelud eruption, I also have like this one. I injected 3 times larger area than the plume itself, And the Kelud, I have to injecting a latitude band of 10 degree or something, which is much larger than that little spot already, but still have hard time to transport meridionally.
Any other questions? Okay, let's thank Yunqian and
Thank you.
thanks everyone for coming. We've got, I think, a seminar in another week or another couple of weeks, but yeah, round of applause now that we're in person.